Hey! In this video you can learn about Hochschild homology and related concepts. Hochschild homology is an invariant of associative rings in general, but we will see that for commutative rings it is closely related to the algebraic Dram complex. This is the content of the Hochschild-Rosenberg or HKR theorem, which we will prove today in special cases. You will also learn about simplicial commutative rings and divided powers in an appendix to this lecture. I'm Achim Krause, I'm from Mathematics Münster, and let's get right to it. So let K be a field and let R be a K algebra. And for us, K algebra means that it's associative, but not necessarily commutative. So in this situation, we define Hochschild homology as follows. The Hochschild homology of R relative K is the homology of a chain complex, which we're simply writing as HH R relative K, which looks like this. In degree 0, it has a single copy of R. In degree 1, it has a tensor product of 2 copies of R, and it continues like this, 3 copies, 4 copies, and so on. And the differentials are given by the following explicit formula, so we have to explain how they work for an elementary tensor like this. And it's given by an alternating sum where we've multiplied certain terms together. The first summand, we've just multiplied A0 and A1 together. The second summand, we multiply A1 and A2 together, and so on. And for the last summand, there's a little twist. There we put the last factor to the front and multiply an together with A0. The way to remember this is to imagine your values A0 to An as being placed along a circle, and then all these maps here just multiply together 2 adjacent terms on the circle. The first one this, and so on, and then the last one these 2. We will see later that this is more than just a picture, and in fact there is a very close connection between this construction and the actual topological S1. Maybe as an example, we take just the easiest K algebra, namely K itself. And if you want to get a feeling for this definition, maybe now is a good time to pause the video and try to work it out in this example for yourself. All right, I hope you tried the exercise. So let's resolve it now. In this case, the Hochschild homology, or rather the complex computing the Hochschild homology, simply has all terms given by copies of K. Right? We take iterated tensor products of K over K. So all of these terms are just K. And these maps basically send 1 to an alternating sum of copies of 1. So depending on whether this is an even or an odd number of summands, you get either 0 or 1. So what you can work out is that this complex explicitly looks like this, where all the differentials are either 0 or the identity. So the homology of this complex is then simply given by k in degree 0 and 0 otherwise. All right. So, of course, we also want to understand what happens for more interesting algebras. And there, it will, in general, be hard to say things about the entire thing, but we can still say some things about low degrees. And so let's focus on the case where R is commutative. Then this first differential here that takes A tensor B to AB minus BA, which in the commutative case is just 0 always. So we immediately get that the 0th Hochschild homology group in this case is just R itself. And the first Hochschild homology group, which is the kernel of this map, which is 0, modulo the image of that map, can be written as a quotient of a tensor product of 2 copies of R modulo the image of the incoming map. And we can describe that quotient explicitly, as we'll see in a second. This is always isomorphic to what's called the Kähler differentials of R relative K. So what is this omega 1 R relative K? Well, let me review it quickly here. So omega 1 R relative K is an R module generated as R module by elements dx for all x in R with the following relations. So we have that d of x plus y is dx plus dy. We have that d of xy is x dy plus y dx. And then finally, since none of this involves k yet, there's also one relation that just says that dx is 0 for all elements that come from k. And you can directly see from this that the map D that goes from R to omega 1 R relative k, it sends x to the element dx, that this is a derivation, and furthermore it's a k-linear derivation. And in fact, a nicer way of saying this is just that omega 1 R relative k is the initial R module together with a k-linear derivation like this. Right. And so what should this map look like? Well, I'm claiming it sends an element of the form x tensor y here to x dy. And the inverse sends an element of the form x dy to this element x tensor y. And since this is generated as an R module by these elements dx, as an abelian group, it's just generated by elements of the form x dy. So these two rules definitely specify at most one map. You just have to check that both of these maps are well defined, that they respect the relations imposed here and here. And if you want to check that, it's maybe another good exercise. Okay, so for commutative rings, we have just now described the degree 0 and the degree 1 part of Hochschild homology. So we now want to also describe the higher groups, at least in certain situations, and for that it will be useful to have some additional structure, namely a multiplicative structure on Hochschild homology. So if R is a commutative K-algebra, we have that the Hochschild homology forms a graded ring so it has the structure of of a graded ring, and in fact a strictly graded commutative ring. So I hope graded commutative is clear. What do I mean by strictly graded commutative? Well, this just means that whenever someone hands you an element x of odd degree, that its square is actually 0. So this is in our current setting, in our current setting, this is of course only relevant if K has characteristic 2, since in a graded commutative ring, squares of odd elements are always 2 torsion. Right. So where does this product structure come from? Well, this Hochschild complex, R relative K, comes from actually a simplicial abelian group, or rather a simplicial commutative ring, rather than just a chain complex. So what do I mean by that? Well, we can write down a simplicial diagram where the entries are just as in the Hochschild chain complex, but the boundary maps are given by just the individual summands without the sign of our differential in the Hochschild complex. So in other words, these differentials just multiply together certain elements in your elementary tensors. And here, so this is a simplicial diagram, and it's not just a simplicial diagram of abelian groups. Here now all these maps are really ring maps. By the way, we also have, of course, degeneracy maps. These are given by inserting ones at certain positions. Let's not make this explicit. So if we have a simplicial commutative ring like this, then it turns out by Ironberg-Silber, Ironberg-Silber theorem, we get a structure as described here on the underlying, on the homology of the underlying chain complex. So let me leave this as is for now, but we will have an appendix to this lecture where we explain this in more detail and where this structure comes from. So now we have this product structure on Hochschild homology, and we've previously compared the first degree Hochschild homology with omega 1. Now it turns out we can also introduce some multiplicative structure on that side by introducing what's called the Dram complex. So we write this omega star r relative k, and this is given by the exterior algebra over R on the Kähler differentials we previously introduced. So this exterior algebra is very naturally a graded algebra. By writing it as direct sum of these exterior powers. But it turns out there's an even nicer way of writing this, namely by taking this R module, considering it as a graded module concentrated in degree 1, and then forming the free graded commutative R algebra on it, which I'm just going to denote as sim. So in the case where K has characteristic 2, this is not quite this, so we also have to enforce that x squared is 0 for x coming from this omega 1 R relative k. And with this description, using that HH0 is just R, so in particular the Hochschild homology of R relative k is an R algebra, and it's graded commutative, and it has this property that odd elements square to 0. So using this presentation of this Dram complex, we get a map from here to our Hochschild homology groups simply by extending the map from omega 1 to HH1 that we started with. The isomorphism that we previously discussed. And now it turns out it's a theorem by Hochschild, Constant, and Rosenberg, which says that under suitable assumptions on R and K, namely that R over K has cotangent complex concentrated in degree 0, then this map is an isomorphism. We will discuss later what the cotangent complex means precisely. For now, we just point out that this property is satisfied in particular for R being a smooth or int-smooth K algebra. Right. So one thing that's worth pointing out here is that this is really just a statement about graded commutative algebras. There is in fact a differential on this Dram complex. It's called complex after all, but that does not play a role here. And in fact, the differential here is degree +1. So Working out exactly what that corresponds to on this side will take up some work later and lead to the notion of cyclic homology. So this HKR theorem we will prove later in the course in more generality, where we allow an arbitrary base, not just a field, and we will discuss in detail what this cotangent complex condition means. For now, we will simply discuss it in the context of a polynomial algebra over K. And a good exercise at this point, if you've never seen the Dram complex, would be probably to work out what, in the case of a polynomial algebra, what this exactly looks like. And in particular, if you have a polynomial algebra in n generators, it's nice seeing explicitly for yourself that this is really bounded by degree n. Before we will prove the HKR theorem in the special case of polynomial rings, we will first extend our definition of Hochschild homology to allow for arbitrary bases. Specifically, we want for K to be not just a field, but an arbitrary commutative ring. And of special interest here to us is the case where K is the integers. We will think of that as the case of absolute Hochschild homology rather than relative. The problem here is that as soon as we don't work over fields, these tensor products over K appearing in the definition we gave for Hochschild homology earlier lead to subtle problems with non-flatness. We will see later in the lecture how to systematically derive everything using infinity categories. For now, we will follow the following ad hoc approach. We will extend our definition of Hochschild homology to work more generally for R dGA over K, which is K-flat. K-flatness is a flatness condition that is a little bit subtle in general, but in the case where R is bounded below, meaning that it's concentrated in, that its homology is concentrated in degrees above a certain degree, it agrees with level-wise flatness. And in fact, you can prove that for the integers, it always agrees with level-wise flatness. So for such a DGA, we can again define Hochschild homology by the same formula as before, where we consider this kind of chain complex. But now note that each of these entries is itself a DGA, so this specifies a bicomplex, and we want to take the total complex of this bicomplex. And as before, we can then talk about Hochschild homology groups simply as the homology groups of this total complex. So if R is not K-flat, we can replace R by a K-flat resolution R flat, which simply means that this is another DGA which does satisfy this K-flatness condition and comes with a map to R, which is a quasi-isomorphism. And having made such a choice, we simply define the Hochschild homology complex as the Hochschild homology complex of this flat resolution. Now in general, of course, this is not well defined as a chain complex because there is a choice made here. But we will see that this does give us something which is well defined up to quasi-isomorphism. One way to see that is to consider the following alternative formula. For a DGA, we have that the Hochschild homology R relative K is quasi-isomorphic to the derived tensor product of R with itself over the derived tensor product of R with R op over K. So some explanations are in order. R op simply refers to the same, the DGA with the same underlying chain complex as R, but the opposite multiplication. If R is, for example, an ordinary commutative ring, this is the same as just writing R, but in general we have to distinguish here. How does this act on these two terms? Well, a module over R tensor R op is the same as an R, R bimodule, since an R op left action is the same as an R right action. And of these deriving steps, you should simply think of as first replacing things by flat DGAs before taking the tensor product. Classically, this is not quite what people refer to as Hochschild homology. Hochschild homology would refer to the same object with the lower tensor product underived. But we will work completely derived in this lecture, and so we will not make this distinction and also call this Hochschild homology, even though in the literature this is often referred to as Shukla homology. So to prove this, note that we can first replace R by a flat resolution. We defined the left-hand side by a flat resolution, so that's clearly compatible with the left-hand side. For the right-hand side, note that since these tensor products are derived, this gives us a quasi-isomorphic result. So after we've replaced R by a flat resolution, we can consider the complex which we obtain as total complex of with a tensor product of two copies of R as a total complex of the bicomplex given by this kind of formula where we have two copies of R in degree 0 and three copies of R in degree 1 and so on. So the differentials here are similarly defined by multiplying adjacent terms together, similar to in our definition of Hochschild homology earlier. But here there is no summand which multiplies the last term to the first one. So if the image you had in mind in the previous definition is on a circle, then you should think of this as somehow given by configurations on an interval. This is what's called the bar complex, and it's a standard lemma that the total complex of this bicomplex is in fact quasi-isomorphic to R. So if we apply this space change here to our complex, using the fact that that each of these terms has a bimodule structure and all the maps respect this bimodule structure, so we can think of this as a complex of R tensor R op modules, then after the space change we get a complex with one factor of R less in each degree, and by directly looking at the differentials, you can check that that complex now is exactly the complex we used for our definition of Hochschild homology. So because of this relationship, this is the complex that appears in the definition of Hochschild homology is typically called the cyclic bar complex, because we've somehow closed the interval up. But it turns out, as bimodules, or equivalently as R tensor R op modules, all these terms are also base changed from flat K modules. For example, this one is just base changed from the K module K. This one is base changed from the K module R, and so on. And in fact, all of these modules are K flat. So this is really a complex of K flat R tensor R op modules, and it follows from the usual description of derived tensor products that the total complex of what we got after taking this base change is precisely this. So after applying this base change, the total complex computes the derived tensor product, since we've exhibited that this is something like a flat resolution of R, but it also coincides with the cyclic bar complex. So it also computes the Hochschild homology. And this finishes our proof. So in this new generality, where we have Hochschild homology of arbitrary DGAs, it's worth revisiting the multiplicative structure. And there's a little subtlety involving this claim of it being strictly graded commutative. The correct statement here is that if R is a DGA which comes from a simplicial commutative ring, again via Ironberg-Silber, the underlying chain complex of a commutative ring, of a simplicial commutative ring, comes with a DGA structure, then the Hochschild homology, and maybe I should say simplicial commutative K algebra, and the Hochschild homology relative K is also comes from a simplicial commutative K algebra. In particular, under these assumptions, we have that the Hochschild homology groups form a strictly graded commutative ring. So right, and maybe also here form a simplicial commutative K-algebra. So the proof is as follows. If we can represent our DGA by a simplicial commutative K-algebra, then the first thing we can do is replace this by an equivalent simplicial commutative K-algebra, all of whose entries are flat K-algebras. This is again some kind of resolution trick. So we may assume that we have a level-wise flat simplicial commutative K-algebra, and with this assumption, we can in fact just apply Hochschild homology level-wise. So if we just take the level n simplicial the commutative K-algebra, the flat commutative K-algebra in degree n here, we can just apply Hochschild homology to that, and we can do that for every n, and this gives bisimplicial commutative K-algebra. Right, we have one simplicial coordinate coming from this Hochschild construction, this cyclic bar complex construction, and the other direction just from the simplicial direction of our original simplicial commutative K-algebra. And now the total complex of this thing, which by definition computes Hochschild homology, sorry, this is also relative K. The total complex is just quasi-isomorphic to the complex associated to the diagonal. If I have a bisimplicial object, I can take its diagonal, and it's always quasi-isomorphic to the total complex. And now if you look at it, the diagonal is clearly a simplicial commutative K-algebra, giving us this result. So we have a very similar lemma that doesn't need, that somehow is a stronger version of the fact that you still have a multiplicative structure if you plug in any arbitrary DGA. You just lose this strictly condition. And in fact, there's a better way of putting this other result. Let's say the following. So if A and B are two different DGAs, then the Hochschild homology of A tensor B, and I'm putting derived tensor product here, reminding you that if your things are not K-flat, you have to first resolve them. Then this is quasi-isomorphic to the Hochschild homology of one term tensored over K, again derived with the Hochschild homology of the other term. if you have a commutative DGA, a graded commutative DGA, like discussed earlier, maybe just coming from a commutative ring, then this statement gives you a product structure, because if you just have A and B both equal R, then here you can put R and R and R and R, and then you have a multiplication map from R tensor R to R, which the composite gives you a product structure. You don't have, the multiplication map is only a map of rings if your ring is commutative. That's why in general, if you plug in associative algebras, you don't get a product structure. But this works for associative DGAs, no assumptions on commutativity. And the proof is very similar to what we did here. So let's maybe go through it quickly. The idea is, again, we can first replace A and B by K-flat DGAs. And we don't have to think about this deriving here. And we can just compute Hochschild homology by the formula we gave. And then both the Hochschild homology of A and the Hochschild homology of B actually come from simplicial DGAs, right? We took some total complex of some some bicomplex, but before we do all of that, we can really write down a simplicial diagram of DGAs for both of these things. And so we can regard this tensor product really as bisimplicial DGA. And it's becoming a little bit complicated because now we somehow have three directions, because somehow every object in my bisimplicial diagram is itself a DGA. If that confuses you, just pretend for a second that A and B are ordinary rings. And then you can really think of ordinary K-algebras here, ordinary bisimplicial K-algebras. But again, the total complex of this, where now we take the total complex in all three directions, is the same, or is quasi-isomorphic to the total complex of the diagonal. And now if you look at what this looks like along the diagonal, then you'll see that the diagonal is precisely the Hochschild complex for the tensor product. So we're now ready to prove the HKR theorem in the special case of polynomial rings. And in fact, as we will see later when we introduce the cotangent complex, that's already most of the work, as we will be able to reduce to that case. We have only defined or stated the HKR theorem in the situation where our base is a field, as otherwise we need some additional assumptions on R. But in fact, it turns out that the proof we're giving basically carries over to the more general statement we will give later. So, by which I mean for polynomial rings over more general bases. So we start by considering just the case with a polynomial algebra on one generator. In that case, the left-hand side of the HKR theorem is simply given by an exterior algebra on one generator over this polynomial ring. So in particular, this is concentrated in degrees 0 and 1. And we've already seen essentially by construction that the map in the HKR theorem is an isomorphism in degrees 0 and 1. So all the HKR theorem is asserting in this case is that Hochschild homology vanishes in degrees bigger or equal to. So let's try and check that. And we will use the formula that we proved previously that expresses this as a derived tensor product of my ring with itself over R tensor R op. And in this case, since this is commutative, I can forget the op, and this is really just a polynomial algebra in two generators, which we're going to name A and B. So this acts on this term and this term simply by sending both A and B to X. So how do we compute such a derived tensor product? Well, we want to check that it's concentrated in degrees 0 and 1. So we're interested in the homology groups, and these are just Tor groups over this algebra with these modules. So how do we compute that? Well, we just resolve this as a module over this. And we have the following very short resolution. Which is just given by free modules in degree 0 and 1, and the map between them is multiplication by A minus B. That's a resolution of the K adjoint A, comma B module, K adjoint X, simply by thinking about this as the quotient of this by the non-zero divisor A minus B. You can also think of this after making some kind of change of basis. You can really think of this as the augmentation map if you make a change of basis and regard this as a generator. Anyways, so if we have a two-stage resolution concentrated in degree 0 and 1, that just means that the Tor groups are going to be concentrated in these 2 degrees. In particular, this shows precisely what we wanted to show, namely that Hochschild homology is concentrated in degree 0 and 1 in this case. So this settles the case of polynomial algebra in one generator. What do we do with a polynomial algebra in n generators? Well, this is just an n-fold tensor product of copies of the first case. And we have just seen that Hochschild homology commutes with tensor products, that the Hochschild homology of A tensor B is the Hochschild homology of A tensor the Hochschild homology of B, at least in a derived sense. And in this case, you can either check that everything is flat or, as I said before, officially K is a field in our statement of HKR so far. So here, the right-hand side of HKR is really just a tensor product of copies of the first case, and you can check either by explicitly computing the Dram complex in this case, or by showing something general, namely that the Dram complex always allows you to pull out tensor products. You can check that the left-hand side is also compatible with tensor products. So both sides commute with tensor products, and that allows us to reduce this case to that case. Finally, we also want to allow polynomial algebras in any number of generators. And this actually follows from this. So R is polynomial in arbitrarily many generators, then we can just write this R as a filtered colimit over polynomial algebras of with finitely many generators by writing the set of generators as a filtered colimit of its finite subsets. So in this case, it follows from the fact that both sides commute with filtered colimits, which for the Dram complex basically follows from the fact that it had generators and relations description. And for the Hochschild homology, you can also check that all of the ingredients that we put into tensor products, taking the total complex, all of that commutes with filtered colimits. So this concludes our discussion of the HKR theorem in the case of polynomial rings. We will revisit this later. Now, as kind of the opposite situation, let us also study a situation which is very much not smooth. So what I want to look at now is the case where we look at fp, relative the integers. Let me give you the statement first, and then we will see how to prove this. The claim is that Hochschild homology of fp relative the integers, and now here we really have to derive, right? The fp is not flat over the integers. Claim is that Hochschild homology here is a divided power algebra. And you could suggestively write this as somehow fp adjoint, or rather somehow the fp algebra with basis given by 1x x squared over 2 x cubed over 3 factorial, and so on. But that's, of course, a bad way to write this, because this is, we can't literally divide by these things. So what this actually refers to is the fp algebra generated by elements x1, x2, and so on, representing these kinds of divided powers, and then the multiplication is given by the relation where xi, xj is the binomial coefficient I plus j over I times x I plus j. And we will simply write this as fp angle brackets x, and think of this as the divided power algebra generated by x. And we will think of these elements xi as x to the I over I factorial, even though in positive characteristic that's not formally true. So how do we prove this? Well, we can use the formula that we deduced earlier, which told us that we can compute this as a derived tensor product of fp with itself over the derived tensor product of fp with fp op over z. Right? And here we really have to somehow work out this thing first. So how do we do that? Well, we can replace fp by a dga. z adjoint epsilon mod epsilon squared with differential d epsilon given by p and epsilon, of course, of degree 1. You can directly check that this is quasi-isomorphic to fp, but this guy is now z-flat. So to compute this tensor product, we can simply replace one of these fp's by that guy and compute the tensor product. And then you'll see that this tensor product, which we're going to denote A to save notational work, that this is really, maybe I should write quasi-isomorphic everywhere, that this is really represented by fp adjoint epsilon mod epsilon squared. And now in this base change, after we've reduced mod p, of course, this differential is just 0. All right. What's left to do now is to compute the derived tensor product of fp with itself over this A. And we can again do that by cleverly resolving one of the factors by a DGA. So we check that if we adjoin a divided power generator to A, again by which we mean that we adjoin x1, x2, etc., modulo the relations xi times xj is I plus j, choose I, xi plus j. And then we put the following differential on it. We say dxi is just epsilon times xi minus 1. And in the case I equals 1, we regard that to mean x1 is just epsilon. And of course, for this to make sense, we have to say that xi lives in degree 2i. Then you can check for yourself that with this differential, the resulting homology is really given by just fp in degree 0. So this is a flat A module which resolves fp. And so this derived tensor product is really just computed by computing the tensor product where we base change this guy along A to fp. In other words, by a free divided power algebra over fp. And the differentials, again, all become 0 under the base change. So this is already the homology, which is what we claimed over here. All right, that does it for today's lecture. We will now come to our appendix on simplicial commutative rings, which were important for product structures on Hochschild homology. A simplicial commutative ring is simply a simplicial object in the category of commutative rings. More specifically, we let the category of simplicial commutative rings simply denote the functor category from delta op to commutative rings. So you should think of an object here as simply a diagram, a simplicial diagram of commutative rings, where all these maps, the boundary maps and these degeneracy maps as well, are ring homomorphisms. So the Ironberg-Silber theorem tells you that the functor that assigns to a simplicial abelian group the chain complex with differential given by the alternating sum of boundary maps is actually lax symmetric monoidal. This is with respect to the pointwise tensor product on simplicial abelian groups and the usual chain complex tensor product on the right-hand side. In particular, this tells us that if we plug in a simplicial commutative ring, we get a CDGA. Note how somehow these individual ring homomorphisms, the individual boundary maps, give the alternating sum, namely the differential in the underlying chain complex, somehow the structure of a derivation with respect to some interesting product structure here. One can explicitly work out what that product structure is, and it is defined in terms of so-called shuffles. So let us make this explicit now and see what shuffles are. So an m, n shuffle is simply a map from the ordered set of numbers from 0 to m plus n to the product of the ordered set from 0 to m and the ordered set from 0 to n. And we will think about this as simply two maps, mu and nu, to this factor and this factor. So it's such a pair of maps with the following properties. First of all, mu and nu are both individually surjective. Of course, the product will not in general be surjective, but individually we require the maps into each factor to be surjective. And also, if you have a surjective map from one finite totally ordered set to another, then it's somehow characterized by at which positions your map jumps to the next element. So we want to say here that mu and nu jump at different positions. Let's say at disjoint positions. So how should you think about that? Well, let's draw a picture where in this picture m and n will both be 2. So from 0 to m plus n we have 5 numbers. And now the set from 0 to m will just have 3 elements. The set from 0 to n will also have 3 elements. And the maps could do something like this. Mu could send the first element to the first element, the second and third elements to the third element here, and the final 2 elements to the fourth one. Note that mu jumps precisely at these 2 positions. So what would nu look like? Well, nu also has to jump at 2 positions, so it has to jump at the 2 other positions. So nu, in order to give us a shuffle, needs to do this. And now if we draw in at which positions these numbers jump, well then let's draw the positions where mu jumps in red, and let's draw the positions where nu jumps in blue. And you will see that at each position, exactly one of them jumps. This is always true under this condition by an easy counting argument. There's m plus n total jumps, and each of them has, like, mu has to jump at n positions, nu has to jump at m positions. In particular, another way to completely specify these two maps is to simply record which of these jumps belong to mu and which of these jumps belong to nu. And this is where the name shuffle comes in, because another way to think of these two different colored, like these segments colored in two different ways, is as a stack of cards consisting of red cards and blue cards. And then that specifies a way to take a stack of blue cards, a stack of red cards, and a stack of blue cards, and somehow shuffling them together in some way. So in this picture, they're somehow interleaved like this, but of course you could have any other ordering of blue and reds, and that would also specify a shuffle. So associated to such a shuffle is also a permutation of cards, right? If you start with the kind of trivial shuffle where first you have all the red cards and then you have all the blue cards, then there's a unique permutation that basically does what you would do if you would shuffle these two stacks together, like you do here. In this case, you'll see that that permutation simply swaps the inner two ones. So the sign of a shuffle, like this, is simply defined as the sign of that permutation. Let's call it sigma. So in this case, the sign would be -1. And now, what is this good for? Well, here's how we can describe the product structure we get on the chain complex associated to a simplicial commutative ring. So let R be a simplicial commutative ring, and then we define a map from Rn tensor Rm to Rn plus m, I should say Rm tensor Rn to Rm plus n as follows. So we will just call this dot, like usual multiplication, and x dot y should be a sum over all shuffles mu nu of size m comma n. It's signed by their respective signs, and then this multiplies together the result of applying the degeneracies corresponding to the surjective maps from m plus n to m, respectively n, applying these to the elements x and y and multiplying them together. You need to do something like this, right? Because what a product structure in the world of chain complexes has the property that if you multiply together an element of degree m and an element of degree n, you get something in degree m plus n. Whereas in this world of simplicial commutative rings, a priori, you only have these pointwise ring structures. It doesn't make sense to multiply elements in two different degrees. And if you have two in the same degree, their product lives in that same degree. So this is how you get into that degree. And the statement is that this formula actually gives R, or more precisely the chain complex associated to R, the structure of CDGA. So let me clean the board and then let's try and see how to prove this. So what do we need to prove? Well, we need to show that this multiplication here is associative, commutative, and that we have this derivation property. And we will in fact see a little bit more. We will see, let me insert that here, we will see that this gives us a strict CDGA, so we will also show that odd elements square to 0. And rather than just going through all the combinatorics explicitly, let me just give you the rough ideas where these properties come from. For example, when you want to check associativity, you have to check that x times y times x and x times y times, x times y times z and x times y times z agree. And it turns out you can express both sides as some kind of similar formula in terms of triple shuffles. So both xyz and xyz are given by a similar sum, which is now over triple shuffles, which are defined analogously, but let's not do that here. But similarly, you get somehow a partition into 3 colors of these jumping positions. And it's similarly signed and involves the 3 degeneracies. So what about commutativity? Well, there you have to check that x, y, and yx agree. And you'll see that since the multiplicative, the product structure, we're showing graded commutativity. So we have to check, we have to compare x, y, and yx, and we will get a sign. And you'll see that this part of the formula, somehow you can swap these 2 factors because you were dealing with a commutative, like a simplicial commutative ring. So if you write down the formula for xy and if you write down the formula for yx, what you get is almost the same formula, just with the roles of mu and mu swapped. And you'll see that you have the same summons, but they differ possibly by a sign. And what is that sign? So let me say same summons up to a sign which is given by the quotient of the 2 signs. Right? If I take an m, n shuffle, I can swap the 2 to get an n, m shuffle. And now I'm comparing the 2 signs. And by explicitly working out this in terms of these permutations, you get that basically that corresponds to the permutation that just swaps a stack of m cards with a stack of n cards. So you can work out very explicitly that this has sign -1 to the mn. In other words, if at least one of our guys has even degree, the sign is positive. If they're both odd, it's negative. So this is exactly graded commutativity. A variant of this argument also gives us strictness. Right? We have to check that if x is of odd degree, that x squared is 0. And in fact, in x squared, you'll see that the summons corresponding to mu nu and nu mu simply cancel. Right? In a shuffle, in an n, n shuffle, you have a corresponding n, n shuffle where you've interchanged the roles. And if n is odd, these will appear with opposite signs in this sum. So all of them cancel, and we have x squared is 0. Finally, to get a DGA, we also have to work out how this interacts with the derivation, with the differential, right? We have to show that the differential is a derivation. And let me not go into this too detailed, but the idea is that the differential is somehow given by this alternating sum of the boundary maps. What a boundary map does is that it somehow forgets one of the indices. And if you forget one of the indices in this term, you're either forgetting it from the part where mu does something interesting or the part where nu does something interesting. And if you work this out explicitly, you'll see that somehow the summands appearing in the boundary of this expression are somehow expressed they fall in two families, which somehow together make up something like dx times y and x times dy. So maybe a good thing to say here is leaving out an index from an m comma n shuffle, mu comma nu gives you either an m minus 1 comma n shuffle, which I'm going to write as mu prime comma nu, or an m comma n minus 1 shuffle, mu comma nu prime, and somehow you can collect these together and express these in terms of dx times y and x times dy. So that's roughly how this product structure arises, how you get these CDGAs from simplicial commutative rings. And we've seen already that you get a little bit more, right? We get this strictness. So it turns out that we also get something additional on even degree elements, namely we get additional structure, so-called divided powers. So let me wipe the board, and then we will see what that's about. So the claim is that if R is a simplicial commutative ring, then we have a divided power structure on the positive degree elements of the corresponding chain complex. What that means explicitly is that we have maps gamma k from Rn to Rnk for each n and k bigger or equal 1 with the following properties. So first of all, gamma 1 is simply the identity. Second, gamma k times gamma L is a certain multiple of gamma k plus L, x, namely k plus L choose k. We have this binomial coefficient appearing. This is why it's called divided powers, because from these two properties you can check that actually x to the k, or x to the n, is simply, or let me say, x to the k is simply 1 over k factorial times gamma k of x. K factorial times gamma k of x. So in some sense, you should think of this element as being something like x to the k divided by k factorial, Although if R is not, say, of characteristic 0 in some sense, if it doesn't embed into its rationalization, then of course you can't really make sense of that in any other way. Right. So furthermore, these gammas need to have some compatibility with the ring structure. So one property is that if you apply this to a sum, then you get this kind of binomial expansion. But since they're divided powers, you don't get any coefficients. You really just get gamma I x and gamma j k for I and j ranging over all pairs of non-negative integers where I plus j is k. So this includes summands where I is 0 or j is 0. I guess we haven't defined them in that case, but by convention, let's just say that gamma 0 just is always 1, right? Which makes sense in light of this property. I guess we could have allowed 0 here and then just said as one of the properties that gamma 0 is always 1. We similarly have a property for products, and that simply allows you to pull one of the factors out to the kth power. So maybe you should think of this as gamma k being somehow homogeneous of degree k. And finally, these compose basically in the way you would expect, namely that if you raise, like if you take the lth divided power followed by the kth divided power, then you get some multiple of the k times lth divided power, and you can work out the coefficient from this. And, well, it's given by this funny expression of factorials. Right. So the statement is that if R is a simplicial commutative ring, then we kind of naturally have these operations with these properties. And again, let me just give you a rough sketch and not go too deep into the combinatorics. So where do these come from? Well, first of all, if x is odd, then we can define gamma 1 of x to be x and gamma k of x to be 0 for k bigger or equal to. And it turns out that does what we want because of the strictness property, right? For example, you need that x squared is 2 times gamma 2x, but since we have this strictness property, x squared for an odd x is already 0, so that's fine. So what do we do for x even? Well, for x even, we look at the k-fold product, right? X to the k. If you think about how we defined the product structure we get on our DGA in terms of shuffles, and how we checked that this is associative, this k-fold product can also be expressed in terms of k-fold shuffles. So you could write this as a sum over mu1 to mu k, where each of these is somehow a map to the set from 0 to n, with these all these disjoint jumps and these conditions. So analogously defined to our twofold shuffles. You similarly have a sign, and then you simply put the product of the corresponding degeneracies here. What you'll notice is that if you simply permute the entries of your shuffle. You get a new shuffle, and it turns out the corresponding summand is exactly the same. Over here, you're just allowed to permute these factors because you're in a simplicial commutative ring. And over here, well, you work out the permutation, and you see, since n is even, that it has sign +1. So one way to think about this is for every permutation of k elements, mu1 to mu k and mu sigma 1 to mu sigma k give the same summand. In other words, we have this action of sigma k on the set of these k-fold shuffles, and along an orbit of that action, we just have k factorial many copies of the same summand, since you can check that this action permuting the factors is actually free on the set of these k-fold shuffles. So what does this tell us? Well, this tells us that if we just pick one summand from each of these orbits, we just pick one representative of these k-fold shuffles up to permutation for each, like we regard two shuffles as equivalent if they can be permuted into each other, and then we just pick one from each equivalence class, and we add those, then we get an element which is kind of 1 over k factorial over this. More precisely, we get an element gamma k of x such that k factorial times that element gives us x to the k. So this is where we get elements from that satisfy that. And now, so this is really sort of how we define our gamma k. We observed that we can group these summands together into groups of k factorial many identical ones, and we just picked one from each of these equivalence classes. Right. And now, of course, you need to do something to check all these properties, and some of them are easier, like this, but some of them are a little bit harder. Let me not do that now. It's all explicit combinatorics. But I would invite you, for example, to think about this one. This is kind of nice. It's related to multiplying, to our discussion of associativity earlier. But well, it's explicit combinatorics. Rather than talking about that, there's another thing we need to address, right? So in the case of the product structure, we also said that it gave us a DGA. So we checked some compatibility with the differential. And that's important because that is the reason why we also get a product structure on homology in the end. And now we have this nice fancy structure, this divided power structure, but none of this involves the differential. So we need to check some more things in order to see that this actually descends to operations on homology. So that's the last thing I want to sketch for you. So what do we need to check? Well, here's the statement. So again, R is a simplicial commutative ring. And we have these operations gamma k on the associated chain complex. And in addition to what we already claimed, we also have the following properties. First of all, d of gamma k of x is gamma k minus 1 of x times dx. And so this is if x is even, and I guess I could write, and it's 0 if k is bigger, or equal to and x is odd, but I mean, we saw already that these maps gamma k are actually 0 in that case, so let's not add that. In particular, if you have an even degree element, which is a cycle, then gamma k of it is also a cycle, right? Because the right-hand side of this equation involves dx. That's not enough to tell you that you get a well-defined map on homology. You also need to say something about boundaries. And here the statement is simply that gamma k sends boundaries to boundaries. Finally, sort of as an immediate consequence of the two, but we can say something about that when we get to it, it follows that the gamma k give a well-defined divided power structure on the homology of R. And divided power structure here simply means that, again, these operations gamma k satisfy all the things they did on the level of the chain complex. The compatibility with the product structure and the additive structure and so on. Okay, so let us try to prove that. Again, I won't be super explicit. So the first property is again something one can check explicitly in terms of the explicit formula. Somehow by writing out the D really as an alternating sum of boundary operators and then thinking about what a boundary operator does to such a shuffle, you can relate these two sides to each other. The interesting part is the second property, because here we're not really giving an explicit formula. Here it's kind of not obvious what one even would need to check. And so let's do that. Let's say x is a boundary. Explicitly, that means that we find some y such that d of y is x, but it turns out we can assume this y to have a special form. Namely, we can write x equals dy for y with diy being 0 for all I bigger than 0. And in particular, then this d really just consists of the single boundary d0 of y. This is something you can easily check by simply starting with any y, such that dy is x, and then subtracting suitable degeneracies from that in order to get a new guy with the same boundary, but this property. For such a y, we are actually able to produce an explicit formula that bounds this x. So how do we do that? Well, we now define an element which I'm temporarily denoting gamma k prime of y. This is not notation that will play any role. It's just that the formula we're writing down looks very similar to the construction of gamma k. Namely, it's again a sum of representatives from this set of shuffles of length k up to this permutation with sigma k, right? We saw earlier on the set of these k-fold shuffles, we have this free sigma k action. We're again summing over one representative from each orbit, like we did for gamma k. So these are again, in particular, shuffles, the same shuffles that appeared in the definition of gamma k of x. So these are, you could say, n, blah, 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 n shuffles, where n is the degree of x. And then we again involve a sign. And then here we're putting s mu prime of y and multiplying these together. And what do I mean by mu prime? Well, in such a k-fold shuffle, as it would appear in the definition of gamma k of x, say x has degree n, then these elements mu I are maps from k times n to n. We can't apply that to y, right? Y has degree 1 degree larger than x. But what we can apply to y is mu I prime, which is simply the map from these totally ordered sets, which are one element larger, that we get from mu I by adding an element at the front. So this is why I wrote 1 plus kn and not kn plus 1. Right, so we are applying those, and then it's easy to check that, first of all, d0 of this element, which remind you, the individual boundary maps like d0 really are ring homomorphisms in such a simplicial commutative ring. So you can compute d0 of this simply by applying it to all of the elements. So d0 of gamma k prime of y, it turns out you can work out, gives you precisely the formula for gamma k of x. That's looking good. And then the other thing you can check is that di of this guy is 0 for all I bigger than 0. In particular, we see that this gamma k prime guy has boundary gamma k of x, proving this. And then finally, we need to say something here, but this really just involves two facts, right? We're saying that if you plug in a cycle, you get again a cycle. And if you plug in a cycle and you change it by some boundary, you get the same homology class. So the latter you can simply check by applying gamma k to a sum of a cycle and a boundary, expanding that using the compatibility between these divided powers and the sum, and then using that gamma k sends boundaries to boundaries. All right, so that concludes our appendix. Thanks again for watching and stay tuned for further videos.